What we have over here is a simulation setup that tries to illustrate what through-the-wall imaging actually does. In through-the-wall imaging, we are trying to find the locations of objects that are concealed from us by some wall or obstruction or anything basically that we cannot see through visually. In through-the-wall imaging, what we do is we send a radar pulse that is that's emitted by an antenna array, which is what you see over here in green. And that radar pulse we use in order to identify the locations of targets. Now, the interesting problem happens when we have that obstruction, because when we don't have any obstructions, if we send that radar pulse, then we can identify the positions of targets without any problem. But as soon as we introduce an obstruction like the wall, now instead of being able to see the locations of the targets that are marked in red, now we see a lot of these ghost targets that come up because of the existence of the wall. And the reason that happens is that when the radar pulse goes through the wall, not only does it go through it completely, but actually it bounces around inside that wall. And then it hits an object or target behind that wall and then returns to the receiver, but also bounces around the wall all over again. And so when the receiver reads the measurements, it thinks that all these echoes are coming from many targets located in the scene. And if we were to just use standard radar imaging, then this is the result. Basically, you think that there's a target at every single one of those sources of reflections. What we do at MERL is we're able to identify what is the reflection that's coming from the wall and what bounces inside the wall, and separate that from the reflection that comes directly from the actual target. So as an example, if we compare the imaging method that we developed at MERL to conventional methods, you can see that with MERL's method, we can completely remove all the noise or all the ghost targets that are in the scene, and we only find the targets that are actual objects located behind the wall. And this technology is actually very useful in situations where you have no way of accessing what's located behind a wall. For example, in the case of disaster relief, if you had an earthquake or a collapsed building, there's no way for you to go underneath the rubble to see if there's anything there. So what you can do now is you can actually send a radar pulse to see what is underneath all that rubble. But it's not restricted only to disaster relief. We actually can apply the same technology to cases where you want to do non-destructive testing. So for example, if you want to figure out if I have pipes behind this wall, but I don't want to break down the wall and have to rebuild it afterwards to see if there are pipes behind the wall. So we can also use this technology to detect this type of situation where you can put your antennas in front of the wall or, for example, above ground. And if we want to see if there's a duct underneath the ground or a pipe underneath the ground, which is what is represented by this square or rectangle, then by sending these pulses, we're able to see the top and the bottom part of that pipe. Whereas outside of that pipe, we don't see any strong reflections. You can see that the technology allows us to clearly identify whatever is behind an obstruction without having to go around to see what it is that's there.